Hello, welcome to episode 5A of Multivariable Physics. And today we're going to be doing linear approximations. And this is going to be very quick. Very, very quick, because it's basically exactly the same as a tangent line. Or a tangent plane stuff. If you recall, if we have some function, right? And we want to approximate it linearly, well, we can just take this linear, so some line at, right? Yeah, we approximate with some line. And that line is really just a tangent line near some point, right? We bound it near some point. It's literally the exact same thing. We just have to think about, so this is the linear approximation principle. If we have some approximation, it's a good approximation, okay? It's good if we have two things. So first of all, f of a is equal to f of a. Okay, so Lx is a good approximation near a for f of x if, okay, here's our ifs. First of all, they're the same at a, because if they're not the same, it's not, not a good approximation. And two, the closer f of x, so as you approach f of x, or I should actually write this here like this, the limit as x approaches a, so our vector x approaches a, we have f of x minus Lx, right, minus our approximation, over the absolute value of the difference between these vectors, or not the absolute value, but the norm. This approaches a 0. Okay, it approaches the 0 vector, or yeah, it approaches 0. If these are scalar functions, right? But what that's essentially saying is, if you have some surface, and we're approximating it with some plane around some point, the closer we get on this plane to FA, the closer we get to FX. So yeah, so in this case, instead of a line, we have a plane, right? And that's all that we're doing. And then actually there's one more thing I want to talk about that I forgot, is the directional derivative. We have extra time, so this is very simple, and we kind of need the plane to think about this. But basically, if we have so directional derivative stuff is going to be here. Oops, I didn't need the directional derivative stuff goes right here. Let's suppose we have some solid, okay, and we approximate with some plane. Here's our plane, okay, and here is f of a. Doesn't matter what that is. So let's say we wanted to know the gradient that's traveling in, or how fast is it moving, okay, in some location, okay? How fast is our thing traveling this way, right? How fast is it going up? Or alternatively, how fast is it going down, right? We want to know how fast this function along the surface, how fast is the surface going, in some direction u. And the way we do that is we can linearly approximate this using this plane. And then all we say is that this is just a small step in our plane. So we would approximate x is equal to a, which is obviously the base of our plane, plus some tiny step u. Okay. And then obviously, remember this, we have our linear approximation is just a tangent line. So I should actually just explicitly write that here. Lx equals f of a plus gradient f of a, and then x minus a. That's what that is. Yeah. And so this linear approximation, if there's a linear approximation, obviously we have to have all these be differentiable over the proper boundaries, right? But if they are, and these two statements are true, then there is a linear approximation, and that is the tangent plane here, right? And so what we can do when we do this linear approximation, we just take the tangent plane, we do this bit to it, and we get f of a plus hu plus this gradient f of a plus hu, I think. Oh wait, no, I messed up. This is actually just f of a. This is not the whole thing. This is just f of u f of a and then this is also f of a. So I should erase that. I'm wasting time. But f of a, and then we have this approximation at L a plus hu, that's what we're doing, equals f of a plus this times hu, right? Because a plus hu minus a, that's all we get, right? So it comes out. And then what we can do is we can rearrange this and then solve for u, or at least, because this is a dot product, we can distribute this h outside, so we end up with this L a plus hu minus f of a over h is equal to the dot product between the gradient at a with u, vector u. And then also remember that because this is a linear approximation, this is actually just f of a plus hu, because we're taking sufficiently small steps, right, within the plane where it's still kind of somewhat accurate, right? It's approximately the same thing. Because as we take the limit, as h approaches 0, well, we get this. And then one thing I also probably should have mentioned is that we actually want to normalize u as well here, so that we're only thinking about this change in regards to h, not the change in regards to u, right? So we're assuming u is normalized. And then that comes out to be what's called the directional derivative of the function there. So hopefully that makes sense. This comes in handy once we look into optimization, things like that. So I think that might be the last one. I think that might be the last bit. It's going to be touching on optimization, and then we might head into physics. Maybe I'll just start doing some physics right away, since I think I covered pretty much everything that we need for now. I should actually mention the notation actually for the directional derivative, which is written so this is actually written as big D of u of f of a. That's what that is. So that's the directional derivative, and then that's just, nabla f dot u, right? Because remember, the gradient is a vector. You can take the dot product. That's kind of what we've been doing this whole time. So that shouldn't be new, right? And we can use this actually to find things. This will answer questions like, steepest ascent or steepest descent, right? How high is this going, or how low? Where, what is the direction of steepest descent and what is the direction of the lowest descent, or of steepest ascent. This descent, this is ascent. This is simply asking the directional derivative, so we can just take this. We just take the vector and we take the dot product and we normalize it, and then we take their dot product. Maybe I'll do some examples. I think I'm gonna finish off with all this stuff, and then I'm gonna finish off the. Actually, this cuts into optimization. So I'll do optimization, and then I'll do some physics, and then we'll still some examples in physics. So that's it. See you next episode.